Hey guys, Professor Doney back again in our last problem with circular motion. Actually, we may do one more next week when we talk about force of gravity, universal gravitation with Newton, and the Earth around the Sun, Moon around the Earth kind of thing. But real quick here, I want to talk about the idea of pulling G's. Now, 1 G is, as we know, 9.8 or 9.81 meters per second squared. So we pull 2 G's, we pull twice that. Alright? So here an example. We're going to be testing you as a pilot, or to possibly be a pilot, and we want to see if you can handle 5 G's. Alright? Because pilots typically, when they're flying and all of a sudden they have to pull up to get away from somebody, they are turning at a radius. That's their airplane. I know it doesn't look like an airplane, but they're going very fast at a radius, and they'll have radial acceleration, which is v squared over r, and because of that high speed right there and not a huge radius because we want to turn quickly, they have an acceleration radially, trying to push them in that way. Now if we take that number, that AR, and divide it by 9.8, it gives us the number of G's, whether we use capital or lowercase, that the person is pulling. Alright? Now, how do they test pilots with that? They can put them in a real plane, but if they pass out, then they have a passed out pilot in a very expensive airplane going really, really fast. That's trouble. So, if you've ever seen, I think it's called Space Cowboys, they put them in a room and they're sort of on this big swing and they strap them in, not like that obviously, but they put them in a little seated chamber and they just spin them around in these circles real fast until they pass out. Okay? Obviously it doesn't look exactly like that, but you get the idea if you've seen that movie. Alright, so we're going to look at that and find out, okay, how fast do you need to be moving around that circle to pull 5 G's. Okay, so let's put your mass in there, or my mass, so I don't pick on you, is 1 kilogram. Let's give it a radius of, we're in a room, I don't know, 6 meters of a radius. Okay, it's, what's that, 20 feet. Not a very small one. Actually, let's make it 8. Let's make it a little more realistic. So 8 would be times 320, or 25 feet of a radius. Okay, and we're going to pull 5 G's. So how do we solve this problem? Well, if we're pulling 5 G's, that's 5 times gravity, which is 5 times 9.8. And if I put that in the calculator here, 9.8 times 5 gives me easily 49 meters per second squared. That is the acceleration I need to experience. So I go to my centripetal or radial acceleration equation. I put 49 on this side. V squared is there. I know the radius we said was going to be 8 meters. If I solve for velocity, that's 49 times 8, and that's 392. We take the square root of that. It's 19.7. 19.8 meters per second. And that's how fast we're moving tangentially. It's sort of what you feel if you get on a merry-go-round and you sit near the outer edge, or you're a spinning ride at the amusement park. When you sit to the outside, you go fast. It's also, if you're in a marching band, the person on the outside has to walk faster than the person's towards the center to make that left turn if you're, in a parade or something. Alright, so that's how fast to be going. Now, what does that mean for spin rate? So you're going to be going over 40 miles an hour there. For spin rate at that distance, we can take that v and go back to 2 pi radius times period, which is 2 pi radius times frequency. So I'm going to put 19.7 on this side, 2 pi on this side, radius of 8, and we'll find the period. That makes, let's see, 6.28 twice pi times 8 equals, we divide that by 19.7, if I did all that right, 2.5 seconds. That means 2.5 seconds for 1 revolution around. That's what period means. Okay? We can get frequency by 1 over that, and I don't have time to do that quickly, but you can. 1 over 2.5 is fraction of a second, so